In this video, we will be discussing the use of Lagrange multipliers to solve linear partial differential equations. So let's consider partial differential equation of the form PP plus QQ equal to R, where small p and small q stands for dou z by dou x and dou z by dou y respectively. Now, capital P, capital Q, capital R, all these can be any functions of x, y, z. Okay. Now, the auxiliary equation in this case, the auxiliary equation is dx by p equal to dy by q equal to dz by r. Now, this relation is also equal to L dx plus m dy plus n dz by Lp plus mq plus nr for any Lmn. That is, Lmn can be any function of xyz. If you choose any function of xyz, this holds true for that. That is, L dx plus m dy plus n dz by Lp plus mq plus nr is equal to all of these relations. Now, to be more specific, suppose if I choose Lmn to be 1, 1, say 0, then this is all of these relations is equal to dx minus dy by p. If I choose Lmn to be, say, 0, 1, minus 1, then this is equal to dy minus dz by q minus r. Similarly, it goes on like this. Suppose if I choose Lmn to be x, y, z, then all of these relations is equal to x dx plus y dy plus z dz divided by xp plus yq plus zr. Okay, these are just some examples that I have taken. Now, this holds true for any Lmn. That is what I was trying to say. But in addition to that, if you choose Lmn in such a way that Lp plus mq plus nr equal to 0, that is, what you have to do is choose Lmn in such a way that this Lp plus mq plus nr is equal to 0. You have to choose Lmn in such a way. Then what will happen is this denominator term will become equal to 0. Now, if that becomes equal to 0, if you equate that with any other relation, you will get L dx plus m dy plus n dz is equal to 0. So what you will get is, you are actually getting, say, dx by p equal to dy by q equal to dz by r equal to L dx, say, L dx plus m dy plus n dz by 0. Now, if you cross multiply the last term with any of the first three terms, then you will get L dx plus m dy plus n dz is equal to 0. Now, as a result of this, what you can do is you can integrate both sides. So, integrating both sides, you will get one solution. Okay, you will get one solution. Now, you have to choose Lmn in such a way that this equation is also integrable. Okay, now you will get one solution. Say, I am going to call it as u of xyz is equal to, say, some constant. Similarly, the second solution, v of xyz equal to constant. This can also be found either using Lagrange multipliers or using method of grouping. So first thing is, you must try whether grouping works. This is the first attempt that you must do. You must try to pair any of these terms together and check whether you are able to solve it by grouping. If it is not working, then use Lagrange multipliers. Okay, Lagrange multipliers, Lmn, you will have to find appropriate Lmn using trial and error method. And even if this denominator does not become 0, sometimes by using some other Lmn, if you are able to solve it, that is also good enough. Now, if you have found these two solutions, u and v, then what you have to do is you have to write the final solution in this form, phi of uv sorry, not q, phi of uv equal to 0. This is the final solution. Sometimes we also write it as u is equal to some function of v, or say some v equal to some function of u. Any of these three forms you can write the solution. You will have the solution will be in terms of a arbitrary function. You have already studied this in the beginning. You can get a PDE either by solving by eliminating arbitrary constants or by eliminating arbitrary functions. If you have phi of uv equal to 0, if you where u and v are functions of x, y, z, then by eliminating this arbitrary function you will get a linear PDE. Okay. Similarly, when you solve a PDE, the solution also will be involving an arbitrary function. Okay, that is what you must know. So you have now found u and v, and the final solution will be phi of uv equal to 0, or u equal to phi of v, or v equal to phi of u. In any of these three forms you can write the solution. Now we will move on to solving a problem. The question is, say x square into y minus z p plus y square into z minus x q equal to z square into x minus y. This is your question. Now what we have to do is, you first write the auxiliary equation. So auxiliary equation, dx by x square, dx by p, that is dx by x square into y minus z equal to dy by y square into z minus x is equal to dz by z square into x minus y. This is the auxiliary equation. This is your auxiliary equation. Now second step is, you just try whether you are able to solve this by method of grouping, at least one solution. Sometimes you will get both u and v using grouping. Sometimes you will only get one solution, u, using grouping. V sometimes you will have to find by method of Lagrange multipliers. Now suppose if I take 1 and 2 together, I am not able to eliminate z from these two. If I am able to eliminate z, then I can integrate both sides and I can find the solution, but we will not be able to eliminate z. Now the thing is, try grouping 2 and 3 together. Then what will happen is, I should eliminate x, but I am not able to eliminate x, so again that is not possible. So the same thing happens with the first and third pair. Now using Lagrange multipliers, I am using multipliers. You can just try for some multipliers. So first, as first choice, we can just use 1 by x square, 1 by y square, and 1 by z square as LMN. Okay, then using these multipliers we get 1 by x square into dx. All these relation, each fraction will be equal to 1 by x square, that is L dx plus m dy plus n dz. So 1 by x square dx plus 1 by y square dy plus 1 by z square dz by 1 by x square into p. So the x square gets cancelled, you will be left with y minus z, plus 1 by y square into q, that is y square into z minus x. So y square will get cancelled, you will get z minus x, plus 1 by z square into x minus 5. So it will be left with x minus y. So all these terms gets cancelled, you will be left with 0 in the denominator. Now from this what you get is 1 by x square dx plus 1 by y square dy plus 1 by z square dz. This is equal to 0. Now integrating both sides, you get integral 1 by x square. So the output will be minus 1 by that is x raised to n plus 1 by n plus 1. So x raised to minus 2 plus 1, which is x raised to minus 1 by minus 1. So I am writing it as minus 1 by x minus 1 by x minus 1 by y minus 1 by z is equal to, say, some constant. That again I am going to simply write it as minus c1. So what I'll get is 1 by x plus 1 by y plus 1 by z is equal to some constant c1. So this is your u of x, y, z equal to constant. Now as a second multiplier, I am going to use as a second multiplier you just have to find these multipliers using trial and error. So 1 by x, 1 by y, 1 by z was 1 by x square, 1 by y square, 1 by z square was simple, because if these terms get cancelled, then y minus z plus z minus x plus x minus y, obviously it will become 0. So that is why we chose 1 by x square, 1 by y square, 1 by z square. So that is how we are choosing LMN. Now if that is, now we have to find one more term. So possibly choose for 1 by x, 1 by y, 1 by z. Then what will happen is x will get cancelled. Here there will be xy minus xz. Here y will get cancelled. If I choose 1 by y as the second multiplier, then we will be left with yz minus yx. Similarly, if I multiply this by 1 by z, then what will happen is zx minus zy. Then also the same cancellation will work. Okay, so I'm going to try the multipliers 1 by x, 1 by y, 1 by z. Now then, each fraction, if I choose the multipliers as 1 by x, 1 by y, 1 by z, what we will have is each fraction is equal to 1 by x dx plus 1 by y dy plus 1 by z dz whole divided by 1 by x into p. So p is x square into y minus z. So I will be left with x into y minus z, that is xy minus xz, plus 1 by y into y square into z minus x. So I will be left with yz minus yx, plus 1 by z into z square into x minus y. So I will be left with zx minus zy. So I have an xy term here and an xy term here which gets cancelled. Now I have an xz term here and an xz term here which gets cancelled. So yz and yz will get cancelled. So the denominator becomes 0. So I will be left with L dx plus M dy plus N dz is equal to 0. So that is 1 by x dx plus 1 by y dy plus 1 by z dz is equal to 0. So what will happen is, now when I integrate both sides, so integrating both sides, I will be left with integral 1 by x dx is log x plus log y plus log z is equal to log, say, some c2. Now taking antilog on both sides, xyz equal to c2. So your v is xyz. In the earlier we had found the first solution as 1 by x plus 1 by y plus 1 by z. Now the second solution is xyz. So your final solution is phi of 1 by x plus 1 by y plus 1 by z comma xyz equal to 0. You can or you can write the solutions like this also. Say for example, phi of 1 by x plus 1 by y plus 1 by z is equal to xyz, or say xyz is equal to phi of this thing. Or you can also write it like this: 1 by x plus 1 by y plus 1 by z is equal to phi of xyz. You can write the solution in any one of these three forms, but I'll be sticking on to this form: phi of uv is equal to 0. This is your final solution. Okay. Now, thank you.